Welcome to the Foundry by Forge College. I am so incredibly glad you're joining me today. We're going to be diving into framing an analytical study of Nakamoto Consensus. Think of this explainer as opening, well, a master detective's case file. We're going to take raw, seemingly chaotic blockchain data and learn exactly how to build an airtight, structured analytical case file out of it. We're moving past just staring at data points and learning how to actually prove something with them.
Now, in our previous lesson, the one covering the impact of Bitcoin nodes on network stability, you did the hard work on the ground. You gathered all this incredible observability data from the network, things like your median peer-to-peer latency and sustained orphan rates. You even mapped the topology. But it leaves us with this big question sitting right on our desks. Now what? What do we actually do with all that data? Well, today is the fun part. We are going to make all that hard-earned data actually mean something real.
Okay, let's dive into this. Here is our investigative roadmap for your capstone report. 1. From metrics to meaning. 2. Defining our threat model. 3. The Monte Carlo race. 4. Drafting your security report. And finally, 5. Proving probabilistic finality.
Section 1. From metrics to meaning.
Any good detective treats raw metrics as their initial clues at a crime scene. They don't tell the whole story just yet, but they're absolutely the foundational pieces we need to build our case. So our primary clues here are median P2P latency, sustained orphan rates, node topology redundancy, and reorg monitoring traces. And remember, these aren't just abstract numbers floating around in a spreadsheet somewhere, right? They are concrete operational inputs. If latency is high, well, block propagation is slow, and that directly affects our orphan rates. We take these inputs to test our hypotheses and create the actual evaluative criteria for our report.
Section 2. Defining the threat model. So, the crucial point is, if we're analyzing a network's security, we need to know exactly who we are defending it against. We have to create a suspect profile. A threat model is the precise specification of an attacker's capabilities. It explicitly states their hash fraction, which we mathematically refer to as Q, alongside any network partition assumptions. You simply cannot prove a network's security without stating exactly what you assume the attacker is capable of. Are they a small solo miner with, say, 5% hash power, or are they a state-sponsored actor with 30%? We have to draw that line in the sand. Section 3. The Monte Carlo race.
All right, now we bring in the heavy forensic machinery. We're going to use a Python Monte Carlo script as our reconstruction tool to really test the network's defenses. I want you to think of block production as a literal foot race. On one side, we have our honest miners. They have a head start in this race equal to Z confirmations, meaning they already have Z blocks officially stamped on the chain. On the other side, we have the attacker. The attacker is desperately running to catch up and overtake that honest chain, and their speed is entirely based on their hash fraction, or Q.
Now, if you read the formal documentation for this simulation, you're going to see it described exactly like this: a discrete Bernoulli model approximating a continuous time Poisson process, which is really just a beautifully fancy, highly scientific way of saying, we're flipping a biased coin to see who wins the next block. Seriously, that's what it boils down to. It's a pragmatic, step-by-step mathematical model that lets us estimate the exact risk of that attacker catching up.
Now, what's really interesting about this is the story these typical Monte Carlo simulation numbers tell us. Let's focus on the bottom row here, where the attacker is incredibly powerful, controlling 30% of the total network hash power. So Q equals 0.30. If the honest miners only have a one-block head start, the attacker has a massive 33% chance of catching up. But watch what happens as we add confirmations. By the time we wait for Z equals 6 confirmations, the attacker's win probability absolutely plummets.
It drops to less than 0.5%. And honestly, this brilliantly illustrates the pure elegance of Nakamoto Consensus. Even if an attacker has a staggering 30% of the hashing power, if you just wait and give the honest chain a 6-block head start, the mathematical risk of a network takeover drops to virtually zero. It's just an incredible defense mechanism.
Section 4. Drafting your security report. Let's move to and see how this all builds together. We have our clues and we've run our statistical simulations, but a detective is only as good as their final report. Structuring complex analysis into a readable, airtight format is a core skill we emphasize here, so here's the sequential workflow for your analysis. First, you define your analytic scope. What exact questions are you trying to answer? Second, you codify the threat model, writing down those precise attacker assumptions. Third, choose your metrics and methods, essentially mapping your latency data to your Monte Carlo script. And finally, step 4, draft your claims with caveats. You state exactly what you found, sure, but you also clearly state the specific conditions under which it holds true.
If you take a screenshot of anything in this explainer today, absolutely make it this quote. Always pair claims with provenance. This is the golden rule of your capstone report. Every single number, every percentage, every claim in your report must have a direct link back to the exact script, the random seed, and the observability file that actually generated it. Because a claim without provenance, well, that's just a guess.
Section 5. Proving probabilistic finality.
This is where we focus on how to interpret our simulated results responsibly, without falling into the trap of making false absolute promises. Look closely at this definition of probabilistic finality. It is a graded property. It indicates risk ranges and sensitivities, not a binary statement of absolute security. See, in Nakamoto Consensus, security is never just a simple yes or no question. It's a dial. Our job isn't to walk into a room and say, the network is 100% unhackable. No way. Our job is to provide operational guidance based on an acceptable, carefully modeled level of risk.
And a good detective always admits what their model doesn't cover. Your report must explicitly state its limitations. Are we modeling coordinated eclipse attacks here? No. Are we accounting for hidden minor collusion beyond the stated hash fraction? No. What about non-Poisson burstiness and block times? Also no. And listen, listing these limitations doesn't make your report weak. It actually makes it infinitely more credible. It tells the reader that you understand the exact, strict boundaries of your evidence. Which brings us to our conclusion, and I want to leave you with a rather provocative question to ponder. If absolute security is a myth, how much probabilistic finality is actually enough for your specific network? Because that is the exact question you're going to need to answer as you finalize your capstone. Thank you so much for joining me for this explainer. To continue your Web3 learning journey and to really dive deeper into this fascinating subject, be sure to visit forge.college. I'll see you in the next one.